We're looking at A-level physics. We're looking at topic by topic. Last time we looked at the speed of sound and we looked at some resonance. I want to move on and have a look at reflection and refraction. Reflection then in a mirror, and refraction, the bending of light. Let's go and have a look at some of these and see what we can do with them. So I've got a setup to have a look at, some ideas of reflection. Reflection, very easy. All we've got here is a mirror, and I'm going to put this on the wall, and I've got an LED light, and if I shine my LED light, we can see that the light goes in, and we're going to call this the incident ray, and we can see the light comes out, and this is our reflected ray. Let's try and see if we can draw this. Now, it's not easy to do this, so I'm going to cheat a little bit, and what I'm going to do is I'm going to draw in my instant ray going in. So I've got my instant ray going in, and I'm just going to basically line this up so it's on there as accurately as I can, and the closer I get this, the brighter the other line. And it's not easy to see that, but you can just about see it. And what I can do is I can then put this ruler on that line and try and get that as accurately as I can. And unfortunately I need to sort of shield this just a little bit from your sight so I can get that more or less as accurate as I can. And it's something like that. Does seem to be more or less on the light. Let's now switch this off, and we're going to do a little bit of cheating here. What I'm going to do is, having pulled the paper out, I'm going to then extend this line down, and I'm going to extend this line down, and what I want to do is draw in a normal. I'm lucky this ruler has got an extra long mark on the 6 which I can line up, and that gives me my normal. I've got a choice, but I'm going to take a simple protractor rather than a full 360 protractor, and what I'm going to do is I'm going to measure this angle coming in, and the angle coming in I had was here, according to this, about 24 degrees. Measuring the angle coming out, (25, 26, 27 degrees. Now, why wasn't that very accurate? Well, it's not very accurate for a whole series of reasons. Basically, this is an LED light, and it's spreading the light out quite a lot, and we can see that that's spreading out here an awful lot. And as long as I'm somewhere within that sort of angular distance, which is what I've got here. If I put my hand over, it's even a bit wider than that. If I'm somewhere in that, then it looks reasonably accurate. I can do better if I swap this with a laser. But the laser becomes slightly harder to see. But if I can position the laser, we can see that this time the line is quite a little bit different. I'm trying to get it exactly on that spot, and that means that line is about there. So let's see if I'm any better with a laser. Going to my point through here. Let's see if I can measure my line again. So I'm going to position my protractor on here, and I've got surprisingly 24 degrees. I'm quite pleased with that, really. So my LED light, not as good as a laser. The laser gives me a much narrower point of view and gives me a much better idea of what's going on. So if we look at this, then we can come up with a simple rule, and that simple rule is going to be, I'm just going to go and write this down for you, that for reflection at a mirror, so there's our mirror, we've got our angle in, we have our normal, we have our angle out, so we're going to have this in and the angle of reflection, that the angle in, which we call the incidence, equals the angle of reflection. And you did that at GCSE and you had no problem really following that and understanding that, and it's relatively easy. We looked at, in our first lecture, we had a look at this with waves, and in the waves what we had was a similar thing. We had our, this time, metal reflective surface, and we sent in, rather than a simple wave, we sent in a series of parallel waves, and they hit and they came out as a series of parallel waves going the other way. We've got our normal, and we can measure this angle going in and we can measure this angle going out, and we find exactly the same, that the angle of incidence equals the angle of reflection. We'll try to convince ourselves this is true by having a look at what happens with a glass block. So if I replace my mirror here with a glass block, what I'm going to do is the same thing. So I'm just going to get my pencil and I'm going to mark where my glass block is. So there's the front of my glass block. We're going to do this very approximately, so I'm going to use my little light here, my LED, and the glass block, it will go through, but very faintly I can see that I've got some sort of reflection at about this point. So we have got some reflection of the glass surface. And if I try to draw this one in, I'll line up my normal, and if I measure this angle, I've got an angle of 35, 36, 37 degrees this side, and if I look on the other side, I've got 35, 36, 37 degrees. I did pretty well on that one. So we've got the glass block, and we have the mirror. And the mirror, it seems, works much better with the laser as opposed to the LED, which I've just recorded on there. So that is looking at reflection. Move that out of the way. Now let's move on from reflection and we'll have a look at refraction. And with refraction, let's have a look at a very simple little experiment, and this will require just a little bit of coordination with the camera. So what we're going to do is I'm going to put up a little arrow. Now with this arrow, and I'm going to get Paul to move the camera along so we're in front of what we're looking at. Now what I'm going to do is, now with the camera in the way, it's alright, no, I want the camera there. I moved the camera where I really needed it. There we are. Having an argument here with the cameraman who was trying to make my life easier for me. Now if I take this glass and I move it in front of this arrow, we will see it's just about getting tipped and changed. Let's lower the camera a little bit. Let's do this on the fly. Now we're going to take the camera down so that we can see perhaps this a little better. And as I move this glass in front of the arrow, you'll see that basically it's getting bent a bit, but nothing happening. Let's now take some water, and Paul's just going to zoom out so you can see what I'm doing. So we've now got a glass of water, and let's now move the glass of water in front, and we're seeing that the arrow is in fact facing the opposite direction. I need to have another hand here, and we can see that the arrow moves in the opposite direction. So what's happening here with this glass of water to cause this to happen? Well, we've all seen this trick where we put in the pencil, and if I get the pencil there, we can see that obviously I've broken my pencil. Yeah, of course we haven't. It's caused by the refraction of the water, which is causing both these things to happen. and if I put the water in, you can see it changes angle. Right, so we've got this idea of refraction. Now, what we're going to try and do is look at refraction in this glass block. And to try and make it easier for you to see, I'm going to have to move my piece of paper with the arrow again so we can see what's going on. I've got a glass block, and what we're going to do is we're going to pass light through this glass block, and we're going to try and see what happens. And to do that, of course, we've got to adjust the camera again. There we go. Right. We need a better system here. Now, what's going on? So, what I'm going to do is I'm going to take a rather wet pencil, and what I'm going to do with my pencil is I'm just going to draw in where this block is. I don't really need the sides, I really need the back and the front. And what I'm going to do is we're going to put in this approximate angle. So let's draw in the angle of my beam of light, and it's going to go in like that. And what I'm seeing is on the opposite side, the light is not coming out where I want it to be, but I can see it coming out. Can you see that? Yeah? I'm trying to see. I can't see, and I can't hold and look. Just tell me if it's okay. Can you see this beam of light here? Mm-hmm. So we've got a beam of light. It's quite wide, but I'm just going to try and mark in a few places where I can see it, and let's have a look and see what's happening. So let's take the block out the way, and if I take the block out the way, we'll see that the light is in fact going without that somewhere along there. So the light has moved. Let's turn the light off and let's draw in our lines so we can see what's happening. I imagine if I set this line up, there we are, it's fitting exactly on that line. I'm going to put in my normal, but this time I'm going to draw my normal all the way through. What we've got is the light coming out on that line, and it should be effectively parallel to this one. I'll try and draw it in reasonably parallel. It's not exactly, but we're within the realms of my inability to draw. And then I'm going to draw up these two lines. I couldn't see that line in the block. We might find that we can try that, and I'm just going to bring this closer. Paul's going to angle the camera down so we're on the block, and if I put the block back where it was and I get the laser out and I get the laser to go down, I can see the laser coming out the other side, but what I can't see is going on anything really through the block. I can't really see anything of the block going on there. I can see the light coming out the other side, following that line, but as try hard as I may, I can't see what's going on inside the block. So let's move the block out of the way. We've got again our angles to play with, and what I'm going to do is I'm going to measure this angle going in. My normal wasn't too bad, and this is 31 degrees. We're going to measure the other side, and this is 15, 16, about 17.5 degrees. And then if I take my ruler and using my long line on my number 6, which I can line up, I'm going to draw in the normal, and if I measure the angle leaving here, it's about 32 degrees. And that probably suggests that my normal wasn't absolutely right. Was not too bad. Probably about half a degree out. So, what are we seeing here with refraction? We can see for this, which is a Perspex block, that the angle of incidence is greater than the angle of refraction. Let's go and have a look at this in a little bit more detail. And I'm going to take this with me. Let's look at what's going on here. Well, we've got my angle of incidence, my angle of refraction, and this is known as Snell's Law. We're going to work out the refractive index of a substance, and I can say that the refractive index of a substance and I'm going to call that N for no other reason than it's normally called N, is the sine of the angle of incidence over the sine of the angle of refraction. Let's see if we can work this one out. So let's call up, let's write down what we're going to do first. So we've got N in this case is going to be the sine of 31 over the sine of 17.5, and if we put that into my calculator, then I've got a problem trying to get my mouse to work. Oh, how boring. Yep, we seem to have a lot. No, there it is, right, okay. So I've got the sine of 31 over the sine of 17.5, and that gives me a number for my Perspex block, which is here 1.712. With the realms of my experimental accuracy, I think we could probably call that about 1.7. No better than that. Let's try this same experiment again, but this time we're going to use a glass block. So we've got our same experiment, but instead of using a plastic block, a Perspex block like this, what I'm going to use is a glass block. My glass block looks a little bit different. You can see perhaps it looks a little bit bluer. It is a different substance. Anyway, so let's see what we can try with this. So, armed with my pencil, I'm just going to draw in the shape of this glass block. It is a very different size, and does that make any difference? You can see it is slightly larger. For those who really like to argue with this, I've got another block which is just slightly larger than the glass block. I don't seem to have two that are exactly the same size. Perhaps these manufacturers need to talk to one another. Right, so let's take in our light, and what I'm going to do is we're going to put the light in at an angle, and I've got my LED working. We're going to try and see what happens. So let's put it at something like about that angle. It'll do. I wanted to push that along a bit. There we are. So here's my light coming in, and I've got my light coming out along this plane here, and it's about there. We can see a little bit more clearly if I put a mirror there. And I tried that so you can just see there is some sort of beam of light going through. Right, so there we've got it. Let's switch off and let's take our measurements to see what's happened. If my light weren't here, my glass block weren't here, my light would just go straight along that line. We're going to put in my normal, and I'm going to go extend it the other way. This line here should be not bad there, about something like about that. And let's see if I can draw this in. I'm not sure I got my normal exactly in the right place there. Let's go and have a look and see what we've got. So if I line this up, then pretty amazing, I've got 30 degrees here. I should have, if we do the normal on this side. If I got this working correctly, 30 degrees there, pretty much, and we'll measure this angle of refraction, and my angle of refraction here is going to be 16, 17, 18 degrees. So it is marginally different to the other one. We'll have a look and see what we've got. So here we're going to have n equals the sine of I 30 over the sine of 18 degrees. Using my real calculator rather than the virtual one this time. Don't think you can quite see that. There we are. So we've got the sine of 30 over the sine of 18, and that's going to give me 1.61. And that is my calculation for that piece of glass, this sort of greenish coloured block of glass, compared with my clear piece of Perspex. So we've looked at a glass block, we've looked at a plastic block. What would happen if instead of this we look at a curved block of plastic? So I've got a curved block, and we can see what this is going to do. What I'm going to do with this one is we're going to set it up like this, exactly the same. So I'm just going to mark it out. And we're going to shine the light through. And sure enough, it's going to do exactly the same thing. We're going to get our light going in, and we're going to get our light coming out. And this is doing the same type of thing as we had before, and we can calculate exactly the same things. Line going in, line going out. Where we really were going out, I can put in my normal. And I can join these two up. And if all has worked out, and this is the same Perspex as the other one, then we should get the same refractive index. So very quickly I can take the angle going in, and this time that's near enough 40 degrees there. Probably 39.5. I suppose we ought to be honest and put it in. Let's do the other line. And much more difficult to try and work this one out. I'm going to cheat. I'm just going to extend that line so I can measure it. And I'm on 21, 22, 23 degrees here. So let's work out our refractive index is the sine of I, which is 39.5 over the sine of 23. Out comes my calculator again, and you should be able to see I've got the sine of 39.5 over the sine of 23, and that should give me here 1.62, which is more or less the same as glass. So I got a slightly different answer. Now, is that a problem? Well, not really. It just says that this piece of Perspex and that piece of Perspex are possibly slightly different. Maybe they are, maybe they're not. What would happen if I did this round the other way? So let's do this same experiment, but this time I'm going to turn the block around. Okay. Shouldn't be any different. So I've got my block, and let's set up a little pointer. And as I turn the pointer round, the angles, they're increasing. So straight through, it goes straight through as I increase the angle. So this is bending more. And we're seeing something else interesting happening here. We're getting now some reflection. I've got some of my line going this way on this point, and I've got some more coming this way. And if I increase this suddenly until we get a point where no light is refracted at all my light is now reflected back this way. And we've got here a mirror on this surface. But we looked at this surface before and there was nothing funny about it. It's here total internal reflection. We can calculate the angle at which that works. We'll do that perhaps in a minute. But let's have a look at total internal reflection first. Let's set the experiment up a different way round. I'm going to take my light and I'm now going to shine it at the camera, and instead we're going to use a piece of plastic like this. And what we're going to do is we're going to lower the camera again. If we'd thought about this before, we'd have probably got the jib out. I want to look at the end here. Now what I'm going to do is I'm going to shine this light down through this block. And what you can see is that the light isn't escaping down this block, but is in fact coming out down this end. You can see that. It's sort of coming out now down the centre. And the light is bouncing along the inside of this light tube. This is total internal reflection. And we can see this in wonderful little toys. And we're just going to have a look at one of these now. Right, Paul's going to zoom out for me, and I've got one of these rather nice things that tend to come out about Christmas. What it consists of is a little light, and there we can see the little light down the tube, and it consists of some fibre optics, some glass, basically some glass fibres, and these hopefully make pretty shapes as they move around. Now if I condense all those fibres together, we can see that light is travelling down there. I can even illuminate part of the paper there, and we can see that not much light here is escaping. Yeah, some is. It's because this is cheap and it's not, fantastic piece of equipment. But this is the principle whereby all your internet arrives at your house, because we can bend these fibres really quite a lot and light will travel down them, and basically your broadband signal is just light travelling down one of these fibres of glass, and as it travels down here you send lots of dots and dashes, and that's your broadband working. Some are lighter, some are darker. That's just because of down on the bottom piece of plastic here that it's not very good, and if that were cleaned up properly it would work more effectively, but it's only a cheap toy. So we've got our total internal reflection used in communications, and it's used in Christmas tree lights. Number of trees I've seen with fibre optics going on. Let's explore what this critical angle is, and to do that we've got our little block again, and I'm going to position this in the same place, and what we're going to do is we're going to try and measure the angle at which this line just disappears, and I can just see it there. You can see on my hand I've got a bit of red there, and if I can just turn this round just a fraction more, it disappears at that point. So let's see what we can measure here. So I'm going to take my little line. There's my line coming out. And we know that the light that was going here was actually just sort of going off in basically that direction. So let's have a look and see what's happening. my light's going in and my light is coming out, and if I can measure this line pretty accurately, it is just about meeting at that point. And what we can do is we can work out what this angle is going to be. I'm going to get my normal done. And if we measure this angle, I've got an angle here of 42 degrees. And that's where on this plastic it appears to be. We should just measure the other side, see if it's about the same. It's not quite. It's virtually 40 degrees there. So there seems to be about my critical angle for this block of Perspex, that we're getting this happening at around about 42 degrees. How about if my block's a different shape? Maybe I've got some triangular prisms. What can we do with those? What I'm going to do is I'm going to try and start with this shape first. Let's take this shape, and what I'm going to do is I'm going to put my light this way through my prism and see what happens. As with all of these, let's start by drawing in my prism. And let's draw in my line. So the line coming out somewhere around about there, and my line going in something about there. Let's see what's happening. I'm going to bring this forward a little bit just so I can reach. Here's my angle going in. Here's my angle going out, and I'm going to have to try and draw these two together because that's the way the light must be going. And if I draw in my normal, everything's always done from the normal. Should be long enough. We can see that if I measure my normal, that this is about 53, about 52. And let's measure the other side. We'll measure the normal. And yeah, excellent. 46 degrees. So perhaps not quite as accurate as I would like, that one to be. Let's do this same experiment though with a different shape prism. What happens with this different prism? You've probably all seen this one, but if I take this here, then what we should find is the light is actually coming out at this point. So we've got the light here coming out in the same direction. You can see my fingers being illuminated as it goes in. What's happening here I need to see that line a little bit better. Yeah, that's not going to work, is it? So let's replace this with a laser because I can see better what's going on. So I've got my prism. We're going to put in the laser light to that point. So we're going to get our laser shining along that point. Let's see what happens. I can't see much light coming out at all here. It is about there. I can see on my finger where the laser light's coming out. So the laser light going in there, and I can see on my finger. Can you see on my finger? No. You can see now on my finger the laser light coming out. It's coming out about that point there. Let's see if we can highlight that with the laser. So what's happening? Not working very well really, but the light is coming out in the same way as it's going in. So it's going in this way, it's coming out that way, and what we've got is, if I've got the light here at 90 degrees, it's just going to go through here, through there, and it's going to get reflected internally from one to the other. And it's not very straight, and the reason it's not very straight is because I wasn't very accurate on trying to put this line in. I was just doing it as best I could. So that gives us some ideas of this idea of refraction. We've looked at then, lost my chair, we've looked at then a whole series of different ideas of reflection of light and of refraction of light. We've seen that in a glass block it's got a different refractive index to a Perspex block, but well, we can worry about those. I always want to do this with a diamond block. What I'm looking for, if anyone's got one, is I'm looking for a nice, doesn't have to be that big, let's say sort of a couple of, well, 2 centimeters by 5 centimeters by about 3 centimeters block of diamond, and I want it, rectangular, And then I could show some really nice experiments with this. Don't think that's going to happen somehow. But it would give us a different refractive index. We've seen that water bends light. Refraction takes place at the surface. So where the two surfaces change, air to glass, glass to water, that's where refraction takes place. We've looked at refraction in a glass block, in a semicircular block, we've looked at it in a triangular prism, and then we've had a look at this idea of total internal refraction, where the light is completely bent, and that gives us some ideas about what's actually happening. We've looked at this and we've got an idea that that was around about 40 degrees. Not too bad. One thing to leave you with is a thought about, how about a rainbow? A rainbow goes into a prism, but it comes out differently. White light goes in, but coloured light comes out. Now, why is that? Well, perhaps you can have a look at one of my videos on this, and you might get some ideas. Until next time, if you found this useful, then please subscribe, and same time next week we'll have a look at some more physics of waves to help you with your A level. Take care, stay safe, I'll see you next time. Bye bye.